So here we're going to talk a little bit about the we're going to talk about the vibrational spectroscopy terms and then look at the different kinds of instruments, the Raman and the IR, and kind of get our mind around the energy level diagram and where the spectrum's coming from. Okay. So we are in the mid-infrared region, 400 to 4,000 wave numbers. We can only collect from 600 to 4,000 in our instrument because we have potassium bromide windows and a potassium bromide beam splitter. We'll explain what a beam splitter is in a second. But that absorbs around 580 or so. And so once it gets below 580, you really have very little light, which means your noise is enormous. And it's not so bad if you're looking at a single beam, but what we're doing is we're taking the ratio, I over I naught. So we're taking a background spectrum and a sample spectrum, taking the ratio. And so when the numbers are really low, some of those numbers are very close to zero, which means you're dividing by zero. And so you get jumps, huge jumps in the noise. And so once you get below 600, the spectrum has such tall noise peaks that your signal is really small if you just plot it. And so that was causing so much confusion for the students. They weren't seeing the peaks because they were plotting the noise, and the noise was going crazy. And so they didn't realize that if that's not the region you're looking for, you can delete it. There's no information there, but it was so hard to convince the students that they could just take data and delete it. But if you're not going to look at 600 and below wave numbers, delete it. It's not of interest to you. So you can just throw that away. That's not where your peaks are. That's just where the noise is. And so I just got tired of fighting that battle. So we set the instrument to collect data from 600 to 4,000. And so we don't have to worry about those noise peaks anymore. But that's why it doesn't exactly match the traditional mid-infrared region. We're only going from 600 to 4,000. Now in the mid-infrared, that happens to be the sweet spot for all of these vibrations. The stretches of our atoms from each other and the bending motions of those atoms. If you get to larger molecules, you might see more very low frequency peaks in the far infrared, and that's the 40 to 400 wave number, but you need a completely different spectrometer. We can't do that with our spectrometer. And then if you get into the near infrared, up to 12,800 to 4,000 wave numbers, we can see that, but we don't have a near IR source. But those would be your overtone spectra, and you would start to see some overtones, and you can get some material properties from the overtones, but not as easily understandable as the mid-infrared. So that's where we are. Now look at the rest of the electromagnetic spectrum. Going left is higher energy, so we get into the visible. Okay, so we're infrared, so we're redder than red. Then we get into the visible. Then we get into the violet and ultraviolet, and that's where you start looking at electronic transitions. So transitions between electrons, especially valence electrons. So the visible region tells us about the electrons that hold the molecule together. So the electrons that are responsible for bonding, the valence electrons, are going to be excited by the visible and UV. So if we want to know about the electron cloud, visible and UV. You want to know about the bond lengths, stretches, bends, what kind of frequency you get from a carbon-oxygen double bond is a ketone or an aldehyde or in an acid group or an ester. Mid-infrared is the place to go. It tells you how the molecules bonded together. And that's why they call it the fingerprint region. Because every molecule, how it's bonded together, is going to be different. Even if the molecular formula is the same. Think about the difference between dimethyl ether. So dimethyl ether, think about that. You have oxygen in the middle, two methyl groups. Or ethanol, an alcohol. Same molecular formula, different infrared spectrum. Because you've got carbon-oxygen bonds in an ether and no OH. In ethanol, you've got an OH and you've got a carbon-carbon bond. So totally different infrared spectrum for two substances that have the same molecular formula. So that's where mid-infrared is a strong suit. Then you get into the electron cloud in the visible region. Then you get into the core or sigma bonds in the vacuum UV. So even beyond UV is a vacuum UV, where you start getting into the sigma framework of a molecule. And then you get into the X-rays, where you start to look at the electrons on just the atoms. So the core electrons are excited in the X-ray region. And you can ionize almost any molecule in the X-ray region, and you can look at transitions in the core electrons of all the atoms. So that's why X-rays are dangerous to us, because they penetrate through and they can cause ions to form in our bodies and facilitate reactions that are damaging to our tissues. Then you get into gamma rays. Most of those go right through us. We don't really interact with them. But they can activate other elements. So gamma activation, you can have gamma rays activate nitrogen and other kinds of metals and then make them temporarily radioactive. So gamma rays can activate iron and then make iron in your body radioactive. And then it can emit X-rays and cascade down. And so you can get sort of radiation doses just from gamma rays. So that's this sort of high-end energy. Going to low energy, we get into the microwave region where we have rotation of molecules. So the whole molecule is rotating. I mean, you might have said, well, wait, I just thought we were talking about rotation of CO in the mid-infrared. Well, that's why if you look at the lab handout and look at the lab for next week, it's called row vibration. It's rotation on top of a vibration. But in microwave, it's pure rotation. You're only rotating the molecule. You're not vibrating it. And that only works if the molecule has a permanent dipole. So if you think about it, light has to have something to hang on to, something to twist the molecule with. So the molecule has to have a permanent dipole or light can't cause it to rotate. So nitrogen and air, symmetric molecule, microwaves go right through it. Okay? That's why the air inside your microwave oven doesn't heat up. Nitrogen is symmetric, oxygen is symmetric. So microwaves go right through oxygen and nitrogen. They hit your food. What's in most of your food, we hope? Water. And it's tuned to the rotational modes of water. So the microwave oven really just heats up the water in your food. And it will drive the water out of your food. That's why it just really gets tough if you cook it too long. So here's my secret for reheating a hamburger patty. Right? One last thing you want is to reheat a hamburger patty and have it be like a boot tongue or a hockey puck. Okay, take a dry Tupperware dish and set it over the hamburger patty so that the steam that leaves your hamburger patty will bounce back and hit the hamburger patty and keep it moist. So just the dry plastic Tupperware, the microwaves go right through it. It's a little pro tip, and you can have a nice moist hamburger patty. So it's important for college students. And then you get to radio waves, which really doesn't have enough energy to do anything useful in terms of spectroscopy, unless we use a magnetic field. And so if you put a molecule in a magnetic field, you might be able to get enough of a magnetic field so that there's an energy difference between things that typically don't have any energy difference, but you put them in a magnetic field and they might have an energy difference. And one of those things is the spin of a nucleus. So there's really no energy difference between spin up and spin down on a nucleus, but you put it in a magnetic field, and this intrinsic spin is like a little magnetic moment. So you have these little magnets. All the nuclei that have spin have little magnets. If you think about it, they're like little magnets. And if you put those in a magnetic field, they can either be with the magnetic field or against it. And so like north and south against each other, that's the low energy configuration. With each other is a high energy configuration. That energy difference is a direct function of how strong the magnetic field is. So if we put protons in a strong magnetic field, we can get this energy difference, and then the radio frequencies can cause that jump to occur. And so that's where radio frequencies really come into play in NMR. So nuclear magnetic resonance. The magnetic field sets up a difference in energy based on nuclear spin, and we can only get that difference to be in the radio frequency. We're really not that strong. Our magnetic fields are really strong, but they're not strong enough to cause those nuclei to split very far. And so the splitting difference is only in the radio wave region. Megahertz, 360 megahertz for our NMR, for our good one. 60 megahertz for our little, tiny permanent magnet one. They have 600 megahertz machines, pretty common at some universities. Then they have these mega NMRs at research facilities. So that's still in the radio frequency wave. It was kind of fun to watch. At UT, they had one that was 100 megahertz. That megahertz is the frequency that excites the proton. UT also at the time had a student radio station, KUT, that was at 100 megahertz. And so they had the probe here hooked to a radio, just a wire that went over to the antenna on the radio. And he had it tuned to KUT. So we're listening to the student radio station. And he's over at the console and he's put in trimethylsiloxane. And so it's got a lot of nice protons on it. And it's sitting in the probe. And he said, all right, let's do a pulse. And he pulsed the radio frequency and it pulsed the protons in that molecule, and we heard it on the radio. And it was like clink, and it sounded like someone hitting a piece of metal. You know, it was like clink, and you didn't really hear much. And he said, now let's shim the magnetic field so that all those protons are in the exact same magnetic field strength. And so he shimmed the magnetic field and punched a pulse again, and it was like someone rang a bell. Bing! On the radio station. And when the signal went away, then the radio station came back, and everybody in the room was like, whoa, that's so cool. Yeah, all those protons were ringing with that radio frequency pulse, and we were listening to it on the radio. We were listening to protons. I'm tearing up. I mean, it was just great. And it's just so weird to think about that, you know, but we have this audio thing, this radio frequency thing that carries the signal on a carrier wave at 100 megahertz, and he just sent that proton signal on that same carrier wave. And it was very cool. So radio waves was pretty useless for a long time until we came up with NMR, and so then we were able to use radio waves. Now in between here, we have between radio waves and microwaves, terahertz spectroscopy. And we haven't done much molecular spectroscopy with that, but that's the frequency range that they're using at the airports. You know, you go stand there at the imager, and it sweeps past real quickly, and so that's using terahertz frequency, which is a little less energy than microwaves. And all that's doing is that it's bouncing that light off of water. And so your body is like a bag of water. And so it bounces off your body's water and comes back to the detector. And it can scan your whole body right away. And your clothes, it just goes right through clothes because clothes are not full of water. And you say, well, what if I had a water bottle in my pocket? It would see it. What if I had something really dense like plastic explosives? It would see it. What if I had a gun? It would see it. You know, so it's bouncing off your body. That's going to be bright, and anything between the scanner and your body is going to be dark. And it's going to be darker if it's more dense. So metals would be very black. Plastics might be less black, but grayscale of some sort. But your body would have a certain shine to it, and then any object under your clothes would show up right away. So what I've just said, basically in words, is on this table, and it kind of talks about the sources. These are the essentials. You should know these equations and be able to do math with them, you know, like the back of your hand. What's new?
C over lambda.
Yeah, C over lambda, very good. Good job. And so here's your constants. Now I've got these constants put out to some ridiculous sig figs. Okay? In the lab, use them all. Okay, because Excel doesn't care about rounding, right? You type in all those sig figs, and if you're going to try to find the bond length of CO out to 4 decimal places, you better not use just Planck's constant to 3, right? It doesn't make sense to use your constants with tiny, tiny little sig figs. So write them out, use them in the lab, put them in a cell and anchor it. I mean, you shouldn't have to type these in but one time in your spreadsheet, and then just keep going back and anchor that cell for all your constants. And that way you have the best precision you can get with your various mathematical calculations. Let's look a little bit at the spectrometer parts. So dispersive instruments, they have a prism or a grating, and they disperse the light, and a lot of times you scan that grating and send the light through a slit with a detector. And so this detector would be back here, and there would be a slit. And so for high resolution, you need to narrow the slits and only let a few wavelengths through at a time. But for high resolution, what does that do? That reduces the amount of light you have. And that increases your noise. Your signal to noise ratio gets poor because your noise goes up or stays the same and your light goes down. So your signal drops, your noise stays the same, and your signal to noise ratio is garbage. Okay. Well, we could replace the slit and put in a diode array detector, which is really very cheap nowadays because that's what our digital cameras are using. Our digital cameras are using two-dimensional displays, but we can make really high-precision single-dimension, or it's like one-dimensional displays, and that would be called a diode array. We could take the slits out, take this detector out, put in the diode array. Then we don't have to scan the grating. We can just take all the dispersed light and shoot it on a diode array. But there, for more resolution, you need more pixels. And that ups your cost, but again, they're pretty cheap. So diode array spectrometers are really very cheap and pretty high resolution. They're fairly noisy. We have that in our Raman spectrometer. So when you were looking at the Raman, it went into this little box over here, and that box had a fixed grating and a diode array detector. So no moving parts. Now they make them on a USB. It looks like a USB drive, but it's a spectrometer. And you can screw in a fiber optic cable, and you can go around and take spectra. Now, why would you want to do that? Well, you have a laptop you take out into the field, and you can take visible spectra of leaves and things. So agricultural applications, field studies, water quality. You can take these spectrometers wherever you want to go and run them on a laptop. But for the infrared, for the Fourier transform infrared spectrometer, we have an interferometer. And so this is a picture of one type, a Michelson interferometer. We have the source. We have a beam splitter. And I talked about that earlier. I said, well, our beam splitter has got potassium bromide, salt. In the infrared, glass is going to absorb infrared light. So we can't use glass optics. So we have to use something that doesn't absorb the infrared in the region that we're interested in. And so we use salt. But we can't use salt with light atoms because those light atoms will vibrate and absorb. So we need to use heavy atoms. So we have potassium bromide. So this window is pure potassium bromide. And it's beautiful. It's clear as glass. But don't touch it because your hands are so moist. You put a big old moistened fingerprint on there and it'll just eat away at the optics. So our beam splitter is potassium bromide, and then they have a little bit of a mylar film on there that reflects about 50% of the infrared light. So 50% is reflected up to a fixed mirror. The other 50% goes forward through the beam splitter to a moving mirror, and that mirror moves back and forth. And we measure with the computer the displacement of that mirror. So the light goes at two different paths and recombines at the beam splitter and produces an interference pattern. So it recombines at this beam splitter, comes through the sample and to the detector. So this is a single beam instrument. We have to take a background and store it, and then we have to take a spectrum and compare the two. So in instrumental, if you're talking about different kinds of spectrometers, you have double beam, single beam, and so on. This is a single beam instrument, and its dispersive element is that beam splitter. Is the interferometer. So we take a background without the sample, then we put the sample in and take a sample spectrum, but we have one detector, one beam path, so it's a single beam instrument. The nice thing about this is 100% of the light goes through the sample, and so we don't have any slits. So we never, for high resolution, have to reduce our slits. For high resolution on the interferometer, we just increase the mirror displacement. And so let me show you how this mirror displacement business works. So here's an interferogram up here. So let me get my pens, kind of go through this. Let's get the highlighter first. Let's see, which one is it? Highlighter. Okay, so this black curve here, this is the interferogram, and it goes down and up. So if you were to look at the raw data of your spectrum, this is what you would see. Now that interferogram that I've traced out shows up as a function of mirror displacement. And so as the mirror moves left from the zero displacement difference, so in the middle is what we call the center burst. That's when both mirror path lengths are the same. And then as the long path, as the mirror displacement moves, it gets longer and then it gets shorter when it goes past. But when it hits the zero displacement difference, just all the lights recombined. And so you set up an interference pattern between, and I've got two cosines here, a red one and a blue one. And so what I'm asking you now is, can you identify which peak goes with which cosine? When we do the fast Fourier transform, it takes this x-axis, which is in centimeters, and inverts it. So we end up with inverse centimeters. And that's how the Fourier transform works. It takes whatever your domain is, whether it be centimeters or time, and it inverts it. So for the NMR, we collect our data with respect to time. And so we have an interference pattern with respect to time. What happens when you do a Fourier transform on that? You get frequency, inverse time. And here we have displacement with centimeters. We do a Fourier transform, we get inverse centimeters. So one of these cosines corresponds to this peak, and one of the cosines corresponds to this peak. And so let's look here. We've got centimeters. And so let's look at the red one. It goes down and up one full cycle in a centimeter. And that's what a wave number is. It's how many cycles you have per centimeter. And so let's call this peak 1. And that's going to be red. Let's switch my pen to blue. This one over here, it goes down at 1 centimeter and comes back up at 2. So how many cycles does it have in 1 centimeter? Half. So it would be this peak over here, and we would have to label that one 0.5. Okay. So do you see that? And then that interference pattern, if you look at it closely, it matches when the red and the blue are in opposite phase, our signal is 0. Right? When the red and blue, like red is negative here and blue is 0, so it's at the smallest value. Here, when red and blue are both back up at their maximum value, then our interferogram is at its maximum value. Now there's also a function that's been applied to this interferogram called a triangle function. And it makes it go smoothly to 0. Because if the interferogram doesn't go smoothly to 0, you get some spectral problems. The peaks bounce at the bottom. They're called feet. The peaks have feet. And so that's called chopping the feet off, or apodization. Apod, no feet. And so that's as far as we're going to get. But that'll tell you what's going on in the interferogram and the Fourier transform instrument.